Hello and welcome to Mandela Effect Earth Changes. My name is Daryl and I'm going to be your host for the next little bit here. Today we're beginning a little mini series. This is the first part and some of you may find it a touch dry. It's just kind of got to be covered though. The carbon dating issue, it gives us some base knowledge that we'll need to really fully be able to subjectively evaluate some of the material we're going to cover, I guess, if you don't have this issue out of the way first. So without further ado, I will get on with some videos here that I want to run through to share some info with you and to try to not there's going to be important notes as we go. So as these important spots pop up, I'll either just insert a quick important note message as like the one in front of you, or we may actually pause the video and have a little bit more discussion on it. Have to see how it goes. You know me. Nothing's for certain. It's all doing her by the seat of our pants. So hopefully you'll like some of the changes here, and hopefully you won't find the information too dry. I tried to pick something a little bit lighter and upbeat, and this really is kindergarten material compared to even the next video coming. So hopefully you can kick back and enjoy, and you don't really need a seatbelt for this one. You will for some of the ones coming up, folks. Alright, to any newbies, welcome, and to all you return riders, thanks for coming back. Here we go with the first little bit.
Nearly every textbook and science magazine teaches that the Earth is billions of years old, and the primary dating method used for determining this is what is called radioisotope dating, or radiometric dating. Now, this is a reliable method for measuring absolute ages of rocks and the age of the Earth, right? First off, many scientists now regard the age of the Earth to be between 4.55 and 4.6 billion years old. Okay, so if this method is reliable and accurate, why the 50 million year discrepancy? That seems like a lot. But let's get into some details here and see what's going on. Keep in mind that there's all kinds of scientific jargon on this topic, and so we'll just present a very straightforward, simplified version of the process. Radiometric dating is the process of estimating the ages of rocks based on the decay of radioactive elements in them. Basically, there are certain kinds of atoms in nature that are unstable and spontaneously decay into other kinds of atoms. For instance, uranium will radioactively decay through a series of steps until it becomes the stable element called lead. The original element is called the parent element, and the end result is called the daughter element. Radioisotope dating is commonly used to date igneous rocks, rocks which formed when hot molten material cooled and solidified. The dating clock started when the rock cooled. During the molten state, it is assumed that the intense heat forced any gaseous daughter elements to escape. It is assumed that once the rock cooled, no more atoms escaped, and any daughter element now found in the rock is a result of radioactive decay since that rock formed. The decay rate is measured in terms of half-life, that is, the length of time it takes half of the remaining atoms of a radioactive parent element to decay. Now, of course, that can be measured in a laboratory, and it is assumed that since we know the decay rate, we can calculate backwards and come up with the age of the rock. But is that all there is to it? Here's where it gets tricky. It's true we can measure a decay rate using observational science, but there's another kind of science that is required to accurately calculate dates for rocks, and that is what we call historical science. Historical science deals with the things in the past, and therefore it cannot be repeated and tested. Dating methods require both types of science, because in order to get accurate rock dates, one would have to accurately know both the decay rate and the initial conditions of the rock sample, right? Since radioisotope dating uses both types of science, we can't directly measure the ages of rocks. There are assumptions involved. For instance, how do we know what the initial conditions were in the rock sample? How do we know the amounts of parent or daughter elements now in that sample haven't been altered by other processes in the past? How does someone know the decay rate has remained constant since the rock formed? The answer is they don't. Let's simplify here and talk about a typical hourglass. Let's say you walk into a room and you see an hourglass with sand at the top and sand at the bottom, and some sand sprinkling from the top chamber to the bottom. Well, observational science would allow us to see and measure the sand, and then calculate how long the hourglass has been running, right? We could make our sand measurements and then calculate when the hourglass was turned over, right? Well, those calculations could be wrong, because we may have failed to consider some major assumptions, like, was there any sand at the bottom when the hourglass was turned over? Has any sand been added or taken out of the hourglass? Has the sand always been falling at a constant rate? Since we did not observe the initial conditions when the hourglass started, and we haven't been watching the sand all the time since then, we must make assumptions. All three of those assumptions can affect our time calculations. Now, of course, there's more to understanding all of this, but enough said.
Okay, hopefully that was pretty light and fun, and at the very least you understand carbon dating, which hopefully I'm sure everybody has heard of. Is hopefully you understand what it is, and you got to understand this is the only method they have. When you hear them talking all these astronomical ages and dates and things, it's all based off this science, off of carbon dating. So I'd just like to take away a few main points from that first clip. Number one, if you remember, it started out saying all our textbooks and teachings tell us. So right there, all the information moving forward is suspect already, because our educational systems, including the textbooks, everything, it's all been hijacked, and it's all being controlled and operated by people with agendas outside of what you believe they are. So it's a good thing to keep in mind as we go. And the other thing I think probably that should have jumped out at most of you is there's a lot of assumptions involved in this science. So, with that aside, let's go take a little closer look at the actual science itself, the steps involved. I've got a sample. I want to go get it tested, see how old this stuff is. So, let's go get more scientific information, we'll call it. All right, see you soon.
I'm Chris Pryor. I'm the team leader for the Rafter Radiocarbon Laboratory here at GNS Science. This is the sample preparation laboratory for radiocarbon dating, and today we're going to show you a little bit about how radiocarbon dating is done. So how does radiocarbon dating work? It's actually pretty simple. All living things contain carbon, and there are three naturally occurring isotopes of carbon: carbon 12, 13, and 14. Carbon 14 is naturally radioactive. It's formed in the upper atmosphere through the interaction of cosmic rays with nitrogen atoms, and that carbon 14 that's been formed is rapidly oxidized as carbon dioxide and gets incorporated into the atmosphere. Plants take it up from the atmosphere as CO. So the C14 is rapidly mixed throughout the environment. Actually, there's a lot more carbon 12 and carbon 13 in living organisms than carbon 14, but all living things are naturally radioactive because they contain carbon 14. As long as an organism is living and breathing and taking in food, then it's in equilibrium with its environment, and it has a constant ratio of 12 to 13 to 14. When an organism dies, it's no longer taking in any new carbon, so at that point the carbon 14 in the organism begins to decay away. That's kind of like the start of the stopwatch for radiocarbon dating. If we can accurately and precisely measure how much C14 is in our sample now, we know how much should have been in the sample when it was alive. We can then use an equation to calculate how much time has passed since that organism was alive, and that's radiocarbon dating. Of course, the tricky part is being able to accurately and precisely measure how much C14 is left, and that's where all the effort in the laboratory comes in. So the types of materials that we normally radiocarbon date include things like wood, plant remains, charcoal from charred wood, animal products like bone or leather or sinew or horn or antler or skin, parchment. Also, archaeological artifacts that are made from plants and animals. The types of things we can't radiocarbon date are geological materials, so we can't date stone or glass, And we also can't date some things that are beyond the dating range of radiocarbon. We can only radiocarbon date back to about 50,000 years ago because of the half-life of radiocarbon, which is 5,730 years. After about 10 half-lives, which would be 57,000 years, the amount of C14 that was originally in that organism is so tiny that we can't really accurately and precisely measure it with most of the radiocarbon dating equipment in laboratories around the world. A typical example of the type of thing we date in our laboratory is this textile. The client sent it to us hoping that it is 1,500 years old or possibly older, but what he really wants to do is make sure that it's not a modern fake. We look at it first under the microscope, and what we're looking for is identification to see if the sample is what it's supposed to be. We also look under the microscope in order to look for any contaminants that have been added to the outside of the sample that we want to remove. The second step in the process is a chemical cleaning of the sample, because what we want to do is isolate carbon that is just from the sample and not from any external contaminating materials. So what you see here is people doing a lot of chemical processes to clean up the sample. In the textile example that we've been talking about, we're going to give it a series of washes with organic solvents, and those solvents will dissolve any greases or fats that have been attached to the sample by people handling it with their fingers. The next step is to convert the solid sample to carbon dioxide, and then to convert the carbon dioxide to graphite, which for measurement in the accelerator. We load the sample into a quartz combustion tube with copper oxide and a little bit of silver wire. Then we put that combustion tube on a vacuum line, and we pump all of the air out of the tube. When all of the air has been sucked out of the tube, we can flame seal it, and that leaves a vacuum on the inside. Once the sample has been sealed into an evacuated combustion tube, it's put into a muffle furnace and heated to 900 degrees. The copper oxide will cause the solid sample to combust, to burn, and will end up at the end of the process, after it's been combusting overnight, with carbon dioxide and a little bit of water inside the combustion tube. The combustion tube is cracked, and the CO2 is transferred through these traps into a small bottle. The first trap is a water trap, and the second trap is where we collect the CO2. The volume of the CO2 is then measured very exactly so that we know how much we got, and then it's transferred into this small bottle here. The final step in the process is making graphite. What we do is attach this little bottle containing the CO2 to the vacuum line over here, and that CO2 is mixed with hydrogen inside a graphite reaction vessel. There's a small amount of iron powder inside the reaction vessel, which is what we call the catalyst. When the hydrogen and the CO2 are heated to a high temperature, the hydrogen will take the oxygens off the CO2 and deposit elemental carbon in the form of graphite on the iron catalyst. A tiny amount of graphite is the end product from the sample preparation laboratory. And now we're taking the graphite from the sample preparation laboratory into the accelerator room for measurement. Albert Zondervan, the accelerator operations team leader, and his team take over the measurement from this point on. The graphite is pressed into an aluminum target holder, and that target holder is placed into this wheel, which has 40 positions on it. In the wheel, 25 of the positions are unknown samples, and the remaining positions are graphites that are made from standards and blanks, materials that allow us to determine our quality assurance and how to calculate the age. At this point, the wheel is placed into the ion source. The source is a cesium beam that blasts the carbon out of its target holder and into the accelerator. The stream of carbon ions goes through the accelerator being bent at certain places by magnets, which serve to separate out the carbon 12, 13, and 14 into separate streams. The carbon 12 and 13 are separated out at this point, and the carbon 14 continues on through the accelerator to this point where it is detected. Once the data has been analyzed on the accelerator, then we have to calculate a radiocarbon age. The information that comes off the accelerator is actually a ratio of the carbon 14 to carbon 13, and we have to use an equation to calculate a radiocarbon age. A radiocarbon age is always reported with a plus or minus error, and that plus or minus error means that the radiocarbon age can fall anywhere within that full age span. So because a radiocarbon age is not the same as a calendar year, we have to use calibration to convert the radiocarbon age to a calendar age span. In this particular case, the radiocarbon age intercepts the calibration curve at two different locations. The majority of the intercept falls within this area here, which is about 400 to 350 BC, but because the outer bounds of the radiocarbon age range intercepts the part of the curve that comes up here, there is a small but significant possibility that the calendar age of the sample could be in the 280 to 230 years BC age range as well. So, while we're not able to determine an exact specific calendar year for this textile, we know that the radiocarbon age range converts to a calendar age range, which shows that it is indeed an antique textile and not a modern forgery. I hope our client's happy with the result.
Carbon-14 is produced in the atmosphere by the sun. It breaks down at the rate of about half of it will break down every 5,730 years. This is called the half-life. So if I gave you a pile of carbon-14 and you waited 5,730 years, half of it would turn back to nitrogen and you'd end up with half a pile. If you wait another 5,700 years, half of that is going to turn to nitrogen. You end up with a fourth of a pile. In theory, it never goes to zero. It goes from half to fourth to eighth to 16th, etc. But plants are always breathing in carbon-14 in the photosynthesis process. They're breathing in carbon. Some of it's carbon-14. Most of it's normal carbon-12. Animals eat the plants and make it part of their body. Probably during your lifetime, you've either eaten plants or you've eaten animals that have eaten plants. That's about all there is to eat out there. And so you're absorbing radioactive carbon into you, just like I am into me, because we're getting it through the food chain. The plants got it from the air got it from the sun. This carbon-14 got into the plants, then it got into you or into the animals and then into you. But either way, we all contain some radioactive carbon. When the plant or animal dies, it's not going to get any more, obviously. So several assumptions are involved in carbon dating. First of all, they assume that the amount of C14 in the atmosphere, the ratio, which is a very small number, is the same found in the plants and animals. For instance, the atmosphere contains 0.0000765% radioactive carbon-14. It is assumed that I have the same. I've never been tested for C14, and I've never met anybody who has. But I would say that's a reasonable assumption, but it is an assumption. Okay. When the plant or animal dies, it doesn't get any more C14, so whatever it had begins to decay. It was decaying while it was alive, but you never noticed it because it's being replenished, so the balance would stay. But as soon as it dies, it begins to go out of balance. So basically, carbon dating is measuring the amount of carbon in the object with the amount of carbon in the atmosphere and getting a balance. If the atmosphere is 0.0000765% and the object you're dating is only half as much, they would assume it's been dead for one half-life. If it's only 1/4 as much, it's been dead for two half-lives. 2 times 5,730. And then it goes to a fourth, to an eighth, to a 16th. So they're comparing the amount in the object with the amount in the atmosphere. This is how carbon dating works. Sounds good, certainly sounds scientific, but it's based on some serious assumptions that mess up everything. It doesn't work. If I told you to fill a barrel with water, but I have drilled holes in the barrel, while you're putting water in, it begins to leak out. So you have a process of filling and a process of leaking at the same time. You have an adding and subtracting going on simultaneously. At some point, you're going to reach a stage called equilibrium. You'll never fill the barrel past that point unless you speed up the input or decrease the outgo, one or the other. Well, Earth's atmosphere is constantly taking in carbon-14 from the sun, and is constantly losing it to decay. So you have the same thing as the barrel. The question would be, how long would it take the Earth's atmosphere to reach equilibrium? Well, when carbon dating was first discovered or invented in the early 1950s or late 1940s, actually, Willard Libby did this, University of Chicago. He said, I wonder how long it would take the Earth's atmosphere to reach equilibrium, because he knew about the equilibrium problem. They said, after doing some studies, it would take about 30,000 years. Basically, if you made a brand new planet Earth, poof, create one, cover it with air, start it spinning around itself and spinning around the sun is going to strike the oxygen, strike the atmosphere and produce carbon-14, and it's going to start decaying. And they said within 30,000 years, the atmosphere would be equalized. You'd reach this point called equilibrium. You're never going to get more C14, and you shouldn't get any less unless something changes in the system. Well, sounds good. I don't know if the number's right, but the concept is. Within 30,000 years, the Earth's atmosphere would reach equilibrium. The problem is, we still haven't reached equilibrium. There's more C14 now than there was 20 years ago. Actually, radiocarbon is forming 28 to 37% faster than its decay. So if we still haven't reached equilibrium, then the Earth is less than 30,000 years old, which is what the Christians have been saying all along. A friend of mine has a website, archy.org. You can get information there about Earth's atmosphere has still not reached equilibrium. There have been a lot of people doing research on this, and we're not there yet. This chart indicates how carbon-14 is supposed to work, in theory. An object that is still alive should be in balance with the atmosphere, which would give you 16, I'm going to simplify this a little bit, give you 16 clicks per minute per gram on your Geiger counter. If you're listening to testing a sample, it'll go click every 4 seconds, click, click. If it's only giving you 8 clicks per minute, then you're assuming it's 5,700 years old. It's been through 1 half-life. If you're only getting 4 clicks per minute, it's been through 2 half-lives. If you're getting 2 clicks per minute, it's been through 3 half-lives. It's 11,000 years old. This is how carbon dating is done. If you test a sample and you find out you're getting 2.5 clicks per minute or 2.9 or something like that, you look at the chart and read over and find the age by the simple calibration curve, they call it. Sounds good. Doesn't work. If you walked into a room and found a candle burning on a table, and I asked you the very simple question, when was it lit? You say, I don't know. It was burning when I got here. Okay. Let's do what's called empirical science, things we can test and demonstrate and weigh and prove, okay? We're going to measure the candle. We measure the height of the candle. We find out the candle is 7 inches tall. Okay. When was it lit? You say, I don't know. Okay, let's do some more science. Let's measure how fast it burns. Suppose we get an Olympic stopwatch and we measure this thing very carefully and find out the candle is burning 1 inch every hour. Now we've got 2 hard science empirical facts. The candle is 7 inches tall. It is burning 1 inch an hour. When was it lit? You still can't tell me unless you make some assumptions. How tall was it? And has it always burned at the same rate? Neither of those assumptions can be proven. They are purely assumptions, okay? If you find a fossil in the dirt, all you know is it died. You don't even know where it died. You just know where it ended up buried, that's all. Now, the amount of carbon-14 could be measured very precisely, and the rate of decay could be determined. But when did it live? I have no idea, and nobody does. Because you'd have to know how much was in it when it was alive, which that would depend on the assumption that the Earth's atmosphere has reached equilibrium, and we haven't. And you'd have to know that it's always decayed at the same rate. Now, if the Bible is right, and the Earth had a canopy of water overhead, like the Bible, I think, clearly teaches in 2 Peter 3 and in Genesis 1, 6, and 7, this canopy of water would filter out quite a bit of radiation, and they probably had a lot less carbon-14 in the original creation than we do today. So if you dig up a fossil from an animal that drowned in the flood, and I don't know if any of these are or not, but if you find a fossil and say, wow, I believe this one, this ammonite, may have drowned in the flood. It probably did. And we want to find out it's got carbon. It probably doesn't. It's been totally replaced by minerals, but let's assume it has organic material. And so we carbon date it. They would assume that it lived in an atmosphere that's just like we have today. Faulty assumption. Not a good idea. Here's some examples of how carbon dating doesn't work. We'll go in chronological order here. Back in 1949, an article came out in Natural History magazine that said the lower leg of a mammoth dated 15,000 years old, but the skin dated 21,000 years old. It didn't work in 1949. 1963, a living mollusk shell, carbon dated at 2,300 years old. Well, here we are 14 years later, carbon dating is still not working. Okay? 1970, this article came out and they said, if a carbon date supports our theories, we put it in the main text. If it does not entirely contradict them, we put it in a footnote. If it's completely out of date, we just drop it. 1971, a freshly killed seal, carbon dated at 1,300 years old. Still not working, folks. Okay? 1975, a baby mammoth was found frozen. Part of it dated 40,000 years old, another part was 26,000 years old, and the wood next to it is 9,000 years old. Still not working in 1975. 1981, they tried it again. This guy said, no matter how useful it is, the radiocarbon method is still not capable of yielding accurate and reliable results. There are gross discrepancies, the chronology is uneven and relative, and the accepted dates are actually selected dates. This whole blessed thing is nothing but 13th century alchemy. It all depends upon which funny paper you read. Still not working. 1984, shells from living snails were carbon dated at 27,000 years old. Still not working. 1985, they took 11 human skeletons, the earliest known human remains in the Western Hemisphere, and they were carbon dated, or dated by accelerator mass spectrometer. All 11 dated 5,000 radiocarbon years or less. Here these things are supposed to be, a 250,000 years old or something. It's not working in 1985. 1992, two Colorado Creek mammoths, side by side, buried frozen mammoths, were dated. One was 22,000 years old, the other is 16,000 years old. Still not working in 92. In 1996, at Berkeley University, they've got the Geochronology Center. Carl Swisher used the most advanced techniques to date human fossils. This article said last spring he was reevaluating Homo erectus skulls found in Java by testing the sediment found with them. A hominid species assumed to be an ancestor of Homo sapien, erectus was thought to have vanished 250,000 years ago. Even though he used two different dating methods, Swisher kept making the same startling find. The bones were 53,000 at most and possibly no more than 27,000. Well, I would like to point out, Your Honor, that is a 96% error. So it's not working in 1996 either.
Okay, there we have it. I don't know. Is it just me, or does it seem a little funny to you guys too now? I mean, probably, I'm sure there's got to be at least a few of you that kind of assumed there was a little more science behind the science than there really is. And it's just, it's not right. It's not, doesn't even fit the proper definition of most areas of science and investigation. So, anywho, that's kind of the main point of the whole thing, is that you understand that carbon dating is basically, like the guy said, fucking 13th century alchemy. It's nothing more, nothing less. It's pure crap by the people that are, well, number one, by the people that are putting that radiation into the atmosphere for you, for one. We'll be expounding on that in part 2, part 3 or 4 maybe. See, actually, I'm not sure. I'm kind of considering squeezing in an extra little part in between instead of going to what I was going to for part 2. I think maybe the next one I might touch on who it is behind a lot of the stuff we're going to be talking about, just to help you, because really, I don't know, like, unless a lot of you people who research some of the stuff we're going to cover yourself and come up with your own conclusions already, you're kind of going to almost be in a believe me or believe them being the whoever it is you believe is keeping you safe from all these things that are happening to you, your government, your whatever. So, anyways, yeah, I don't know. I'm really considering maybe introducing you to some of those might be helpful, but it might just get us sidetracked too, because they're coming at the end too. They come at the end every time we go through this little cycle we're in. So anyways, that's the summary of it. There you have carbon dating, all these specific dates they give you all the time with the ages of our Earth and the universe and all this stuff. They're talking out their ass. They have no idea. They can guess, but they don't even have any interest in making an accurate guess, because you guys, you just don't get the absolute comprehensiveness of the lies that are our life. Like, it's unbelievable. And that's why the series, I gotta slowly walk yous all through a lot of little things that are overlooked, obviously, I guess, by everybody. But that's what we're gonna do, is just try to share some truth with you, and hopefully some of it'll catch. And now that we have this date issue out of the way, so as we move on to the other stuff, you'll hopefully be able to catch a little bit more of it. So, alright, you folks enjoy, and have a great day or night, whatever it is, wherever you are. Bye-bye.